confirm if you can hear me clearly. Is everyone hearing me clearly? Great. So I need somebody to confirm, probably by talking, if you can hear me clearly. Also, I want to make sure my network is fantastic. So is everyone hearing me clearly? Is everyone hearing me okay?
I can hear you.
Thank you so much. Thank you for confirming that. I want to welcome everyone to join the lab session today. Of course, today lab session is a combined class for 4101 student and 5101 student. Of course, it's going to be a combination of what we did in chapter 3 and some in chapter 4. And I need you to pay attention. And what we're about to do right now may actually provide a clue to how to navigate a path in ongoing assignment. So I'm going to start with all these problems are extracted from the recommended textbook, the textbook we're using for this course, which is already published on Canvas. Now let's start from problem 3.34. The problem 3.34 is centered on discrete probability distribution. As you can see, you are given the possible values of random variable y with a corresponding probability, as you can see. So the probability, is actually this guy, and these are the corresponding the values of the random variable. Now, this has to do with a manager of a stockroom in a factory, has constructed the following probability distribution for the daily demand, the numbers of times used for a particular tool, okay? And it costs the factory $10 each time the tool is used. And the question is, because we live in a stochastic world, we live in a probabilistic space, they want us to figure out the mean and the variance of the daily cost for use of the tool. So if you want to now, solve this problem, the very first thing that you actually need to do is you need to first figure out what does it mean? How can I find the expectation of y? Of course, for discrete random variable, the expectation of y, you're actually going to make use of the formula here. Y start from 0 to 2. So which means you're going to multiply that guy by that guy, that by that, by the past. So what you're going to do is, you're going to be 0. So the 0 into zero point 0.1 plus 1 into 0.5 plus 2 into 0.4. And here you're going to have 0.5 plus 0.8. So that mean is 1.3. The expectation of y is 1.3. Okay. Now, if the expectation of y is 1.3, and they say that it's going to cost the company $10 each time. Now, the $10 each time that they talk about is more or less like they're trying to say z equal 10y. Okay, z equal 10y. Then I want to find where does z represent the cost. Okay, Now, then I want to figure out the expectation of a z. Okay, expectation of a z will be expectation of 10y, and then it's going to be 10 expectation of y, which is what we're doing here. So 10 expectation of y, and you have your expectation of y. All what you're just going to do is to multiply 10 by 1.3. Multiply 10 by 1.3, that's going to give you $13. So which means on average, this company is expected to using the tool here, on average is going to cost $13. Then you're going to do the variance. Okay. Now, if I want to do the variance of that, okay, don't forget, the variance of 10y is actually going to be 10 squared variance of y, which is going to be 100 variance of y. Now, you now need to remember, how do you find the variance? Okay, how do you actually find the variance? Now, I'm gonna remind you on how we find the variance, because you need the variance of y here now. If I have a probability distribution table, I want to figure out y. Okay, so the variance of y is going to be, don't forget, expectation of y squared minus expectation of y all squared. Now, expectation of y squared for discrete random variable is going to be summation y squared, the probability of y equal to that. Like in this case, y start from 0 to 2, okay, minus, you've already gotten the mean. The mean is 1.3, 1.3, then you square that. Now, what you need to do here is you actually need to be squaring. I'm going to square the random variable, then multiply by its probability, plus 1 squared times 0.5 plus 2 squared times 0.4, then minus 1.3 squared. So whatever you get is actually going to be your variance of y. Now, the moment you get that variance of y, you're going to plug that in here. You multiply by 100. So when you multiply by 100, you're actually going to get the variance associated with the daily cost. Is there anyone who doesn't understand exercise 3.34 before I move to the next question? Is there anyone? Okay, silence implies that you get it. Now this is being recorded. Okay, this is being recorded. I'm gonna share my recording on my YouTube channel. Okay, so that is how that's done. Now I want to move to the next question. Now I need you to take a look at this next question. Is theoretical. It said let y denote a geometric random variable with probability of success p. Show that for a positive integer a, the probability of y greater than a equal q raised to power a. And b, show that for a positive integers a and b, the probability of y greater than a plus b, giving y greater than a equal q raised to power b, and all equal to probability of y greater than b. So which implies that, for example, the probability of y greater than 7 giving y greater than 2 is the same as y greater than 5. And why do you think this property is called a memoryless property of a geometrical distribution? You can leave C apart, so we're only going to focus on A and B. Now let's see how this part is going to be navigated. And I need you to pay attention. Please pay attention to what I want to do right now. Okay. Now, we want to find the probability of y greater than A. Okay. Now, if I want to find the probability of y greater than A, they want me to use a geometrical distribution. Don't forget, in geometric distribution, the probability of that equal P Q y raised to power minus 1. Okay, y raised to power minus 1. Okay, now this is the probability distribution that I want to use. Okay, now I'm gonna plug that in now for y greater than a. Y greater than a means, okay, if I want to find the probability of y greater than a, it means I'm gonna sum. Okay, I'm gonna sum the distribution. Okay, and I'm gonna start y is because y greater than a, the next is gonna be a plus 1, then a plus 1 to infinity. That was why you're actually seeing this guy here, because they say y greater than a, the next is going to be a plus 1. Okay, now I want to work on this guy now. Okay, this is what I have. Okay, now if you take a look at what I have here, okay, where I have y star from a plus 1, all the way to infinity. Okay, now if you make an attempt, to plug in where you have, y, if you plug in a plus 1, okay, here, a plus 1, okay, minus that one, you're actually going to see that what that is going to cancel that, and you're only going to have q raised to power a. Okay, so having q raised to power a. So what I'm trying to say, in essence, is that this particular guy here is going to be the same as this guy, because you're actually now going to see that this is another discrete. So if you take a look at this guy, except that y is starting from 1. So y is starting from a plus 1. We make you to have q raised to power a that is going to come out. At the moment that happen, okay, if you take a look at what you have here, what is the sum of a probability? Because that guy, after the summation, is a geometric probability distribution. The sum of probability equal to 1. So 1 multiplied by q raised to power a is still going to be q raised to power a. And that was how they got q raised to power a. So if you plug in y to be equal to a plus 1, the four first gonna have you're gonna have that. Anytime you plug in y equal to a plus 1, it's gonna give you another geometric series that start from s equal to 1. And that was why we have that. Now the next that we want to do now, using the geometrical series, please I need you to pay attention. Can we find this? The probability of y greater than a plus b, given that y greater than a. Now if I want to find that, you remember the probability of A given B in conditional probability, which is going to be A intersection B divided by the probability of B. In this case now, okay, it's more or less like my A is y greater than A plus B. And my B is actually y greater than A. That is what it means. Now, uh, when you take a look at the joint, this is the joint of the two. Okay, you having y greater than a plus b. You can put a comma, y greater than a, or you put an interception and divided by the probability of y greater than a. Now, we now need to, like, if you take a look at, give me 1 second. If you take a look at what you have here, can we find the interception between this and this? What do you think they're going to have in common? Okay, what is the point of intersection between y greater than a plus b and y greater than a? Let me give you an example. Okay, if somebody say, what is common between y greater than 5 plus 2, okay, and y greater than 5? Okay, obviously the one that is common between them is going to be the biggest, the upper one, this one. Okay, because y greater than 5, okay? The point of intersection, y greater than 5 here is also inside y greater than 5 plus 2. So because of that, I'm going to say the intersection between this is going to be just this guy. Look at that. It's going to be that guy. Okay. Now, if that is what you have, I need you to pay attention. Okay. Now, if that is what you have, like I said, you see what we're using? We're using conditional law. Now, now, if you look at what you did in one, the probability of y greater than a, it's equal to that, right? Then the probability, okay, of y greater than that is actually should be q raised to power a plus b. Because if you take a look at this guy here, the probability of y greater than a is actually q raised to power a. Then the probability of y greater than a plus b is going to be q raised to power a plus b. Then the probability of y greater than a is that. So all what I'm just going to do is to simplify that guy. Of course, so this guy can be written as q raised to power a, q raised to power b, divided by q raised to power a. Okay, so if I cut that guy, then I'm actually going to have q raised to power b. Is there anyone who doesn't understand how to figure this out? Okay, now you actually gonna see. So that is for that. Now I quickly want to move now to 3.75. Now, but before moving forward, I need somebody again to confirm if you're still hearing me clearly. Is everyone still hearing me clearly?
Yes.
Okay, thank you so much. In case anybody want to ask question, of course, you can ask your question. Now, if you take a look at 3.75, okay, it said the probability of a customer arrival at a grocery service counter in any 1 second is equal to 0.1, assuming that customers arrive in a random stream, and hence that an arrival in any 1 second is independent of all others. I'll find the probability that the first arrival will occur during the third one, during the third 1 second interval, and the second one said will not occur until the last, until at least the third 1 second interval. Now, if you remember what we did in class, we actually talk about geometrical distribution, and of course, the geometrical distribution, we talk about the probability of how many binary trials I'm actually going to have, before I record first success. I want to believe you remember that. And of course, here is actually centered. You take a look at the question here. It's talk about find the probability that the first arrival, okay, the first arrival will occur during the third one, or second interval. So because this actually is centered on that, so yeah, the idea of a geometrical distribution is actually gonna be full display. So what you're gonna do now, you remember the probability in a geometrical distribution, the probability of a random variable equal to realized value. Actually, you're gonna have it as p or q raised to power y minus 1, okay, where y start from 1 to all the way. And of course, they've given you what your p represents. Take a look at that. So p equal to 0.1. Okay. Now, if your p equal to 0.1, don't forget q equal to 1 minus p, right? Which is going to be, that is going to be zero point 0.9. Okay. So that is going to be zero point 0.9. And what do they actually want you to do? Oh my God. They want you to find the probability of y equal to 3, because, they said the first arrival will occur during the third 1 second. The third, that very third means y equal to 3. So I'm going to use this guy now. So, I want to figure out the probability of y equal to 3. Of course, my p is 0.1, okay, and q okay, is 0.9 that I just computed raised to power 3 minus 1. Okay, I needed to pay attention, to all of that. So right now, so I'm actually going to have point 0.1, okay, 0.9 raised to power 2. So what I want to write here, okay, I want to write raised to power 2. Okay, so point 0.9 raised to power 2 times point 0.1, okay, is going to give you 0.081. In exam, if I set question that has to do with discrete probability distribution, nobody's going to tell you whether it is geometric or it is binomial or it is hypergeometric or discrete uniform and so on like that. So you be the one that will figure it out from the question. So I know that this is going to be geometric because they said find the probability that the first arrival, okay, will occur. Okay, so whenever they talk about, the first sources, okay, in a series of Bernoulli trials, of course, you should know that the probability distribution of interest should be geometric. Is there any question on this? Is there any question? And of course, in the ongoing assignment, there's a question that also centered on geometrical distribution. Now, I'm going to clean my whiteboard. I'm going to clean the board right now. I'm actually going to go to the next question. The second one said, find the probability that the first arrival will not occur until at least the third one. Okay, until at least the third one. When we hear until at least the third one, at least it means, probability of y greater or equal to 3. That's what we mean by at least. There's a difference between y equal to 3, y less or equal to 3, and the y greater or equal to 3. So here it is exactly talking about exactly here. You're talking about at most here. You're talking about at least here. Okay, and of course, for discrete random variable, you can also have a situation, okay, we are y less than 3 or y greater than 3. Okay, so you need to be able to understand, how to interpret that probabilistically. Okay, so y greater or equal to 3. So if y is greater or equal to 3, okay, all what you just need to do if I were you, okay, so what I'm going to do, share, give me 1 second. I'm actually going to clean my whiteboard now. So what I'm actually going to do here, when I say at least 3, I can rewrite this guy using the law of complement. I can say it's 1 minus the probability of y less than 3. Okay, I can do 1 minus y less than 3 using the law of complement because of y greater or equal to 3 and y less than 3 are mutually exclusive. So now here now, when the y less than 3, okay, I'm actually going to do the probability of y equal to 1, okay, because less than 3, I'm going to do the probability of y equal to 2. Okay, because don't forget the geometric actually start from, if I have the probability of y equal to this, I'm actually gonna have p or q raised to power y minus 1, and of course is y is gonna start from 1 2 all the way. So what I'm actually gonna do, I'm gonna use this to find the probability of y equal to 1. I'm gonna also use it to find the probability of y equal to 2. I'm going to add them up and I'm going to subtract from 1, and that will give me that result. Okay, so I'm actually want to move right now, like I said, that question centered on geometrical distribution. Now I want to go into another question. Here they said 20 identical looking packet of white power as such that 15 contain cocaine and 5 do not. Okay, some say 15 contain cocaine and 5 do not. Of course, you should be thinking in direction of success and failure here. Okay, now 4 packets were randomly selected and the contents were tested and found to contain cocaine. 2 additional packets were selected from the remainder. Oh my God. When you hear about from the remainder, it's like after selecting some, they don't replace them. Okay? It means they don't replace them. Now the question now, as said, two additional packets were selected from the remainder and sold by undercover police officers to a single buyer. What is the probability that the six packets randomly selected as such that the first or four or contain cocaine and the two sold to the buyer do not? When you take a look at this question here, because you have two possible outcome. The two possible outcome, is either, the packet, what was tested contain cocaine or not, and the fact that they are using sampling without replacement, your mind should go towards hypergeometric distribution. Okay, the difference between the hypergeometric distribution and binomial is a mode of sampling. Okay, geometric hypergeometric distribution use sampling without replacement, while binomial do sampling with replacement, but the similarity between the two is the focus on two possible outcome. Okay, now because it's an hypergeometric, this is my solution here. You remember the way we actually did this in class, and of course this is the solution that I provided. Of course, I define A to be first selected packet contain cocaine, and the second B is do not contain cocaine, and of course I'll go all the way to find what I have right now. But you know what? You can also use the one we use in class. Okay, like for example, if I have the probability of y equal to y for hypergeometric, I can have a k, which is going to be the totality of cocaine in general, and x is going to be the one in the sample. Then I'm actually going to have n minus k. Of course, the n minus k is the one that do not have cocaine, and n minus s, the one that do not have cocaine in the sample, then divided by k combination n. Okay, so I can also use this approach. Okay, so because of my time, I'm actually gonna move. I'm gonna move. Okay, now you remember in class I walk you through the moment generating function. So which means, for any probability distribution, they can ask you to obtain the moment generating function. So when you take a look at this now, they're focusing on binomial. Okay, it could be geometric, it could be whatever. How are you going to get the moment generating function? So they wanted to show that that of the binomial is going to be equal to that. And of course, the moment generating function. Okay, here the random variable is actually y. Okay, random variable actually y, so it's going to be expectation of this here. Okay, for discrete random variable, binomial is a discrete random variable, then I'm actually going to have a summation, raised to power that, and of course the distribution. Okay, and don't forget the binomial, still the state space is from 0 to n. Okay, so that's exact. So here I'm like, you put a binomial form. So if you take a look at that, that's what I'm doing here. Okay, and then you actually put the binomial distribution. And of course, if you check what I did in class, I think I already solved this guy in class. Okay, I derived that in class for you. You can follow what we did in class for that. Now, but when you have a moment generating function, how do you derive the expectation of y? And how do you derive the expectation of y squared? I need you to pay attention now. Okay. Now, before you're going to, if I were you, if you want to know whether your moment generating function is correct, when you plug in 0 for t, it should give you 1. Okay. When you plug in 0 for t, it should give you 1. And of course, if you take a look at this guy now, when you plug in 0, okay, for t, of course, e raised to power 0 is 1, p plus q, right? P plus q is 1 because the probability, p is the probability of success and q is probability of failure, and 1 raised to power n is going to be 1. So which means this is a through moment generating function. Now, if I now want to find the mean, okay, the mean, you're going to do the first derivative. Okay, you're going to differentiate the moment generating function. Okay, now I need you to pay attention. Here you need a calculus. I have a moment generating function given here. Then you know what I'm doing here? Give me 1 second. I'm actually differentiating that. I'm differentiating that with respect to t. And it's very easy. Okay, if I want to differentiate this guy now, okay, if I want to have n prime of t, okay, the n, that power is going to come down because that's a composite function, right? I'm going to differentiate what is inside it. What is inside is going to be that, and I'm going to rewrite all of that. I'm going to rewrite this now, okay? All this to power n minus 1, which is what I'm doing here. Can you see that? And you now need to plug in. So after differentiating that, you're going to plug in t to be 0, okay? So which means if I have n prime, okay, of 0, okay, the n prime of 0 is the expected value of y. After differentiating that, and I plug in 0 for t, then it's going to give me np. Okay, you can try that. Okay, like here now, you plug in t for 0. Wherever you see t, you plug in 0, then you're going to end up in np. Okay, so that is how we do it. Is there any question on how this is done? I want to confirm again if everyone is still hearing me clearly, because I want to be sure because of my network. Can somebody confirm that? Are you still hearing me clearly?
Yeah, we still hear you.
Okay, thank you so much. Thank you for confirming that. From time to time, I'm actually, gonna ask you a question, to be sure you are hearing me clearly. Okay, now, if after getting the mean, how do we get the variance? From the formula of variance is expectation of y squared, okay, minus expectation of y or squared. Okay, now in terms of moment generating function, it means why can't you differentiate the moment generating function second time? Okay, when you differentiate second time, then plug in 0 minus differentiate only once. Okay, plug in 0, then you square all of that. Okay, now and you've been able to get this guy here, of course, that you have gotten NP for that, want to square that, but you need to figure out the second derivative. Okay, so what I've differentiated before, right? I want to differentiate that again. This is the result of the second derivative. So if I were you need to revisit your the way calculus, basic calculus. So here I'm using a product rule, and of course second derivative we actually lead to this. Okay, so which means when the when after getting the second derivative and you plug in t to be 0, this is going to be expression for expectation of y squared. And of course you getting your variance is actually you're gonna do np squared into n minus 1 plus np minus np or squared. Okay, the rest is just you simplifying that. You simplifying that. Oh my God, when you simplify that at the end of the day, you actually going to get your variance, which is exactly what they are doing here. Pay attention to this guy. That's exactly what they are doing here. Okay, you're actually going to simplify that. Simplify that will lead into NP into 1 minus P. Okay, so that's how that is done. Now I'm gonna move right now. I'm gonna move right now. Let's now take a look at this. If you can be given a moment generating function and they ask you what is the expected value of y, what is the variance of y, and what is the distribution of y. Okay. Now, when I say what is the distribution of y, every distribution has a unique moment generating function. Okay, from a moment generating function, how am I going to figure out the distribution of a random variable? Now, let me tell you this. If I want to find, you're given this as a moment generating function, and they wanted to find the expectation of y, you need to do the first derivative. Okay, after doing the first derivative, then you're gonna set 0 for t. Now I want to differentiate this guy. Okay, so right now if I write m prime, okay, m prime of y of t, then it's going to be 1 over 6 e raised to power t, because differentiating e raised to power t is still going to be e raised to power t, okay, plus, okay, differentiating this guy now, okay, oh my God, I'm going to have 2. Don't forget, you have a 2 over 6 initially, and this is e raised to power 2t, okay, plus, okay, I want to differentiate that guy, the 3 is going to come down, then I'm going to, don't forget, that's a 3 over 6 right here, and I'm actually gonna have this guy here. Okay, now I need to simplify now. Okay, I need to simplify now. Okay, so what I got, so prime of y of t, okay, equal, I got e raised to power t divided by 6, okay, plus maybe 4 over 6, okay, e raised to power 2t, okay, and 9 over 6 e raised to power 3t. Okay, so this is what I have after differentiating that. And after differentiating that, so if I want to get the mean, okay, the mean is just going to be, what you have differentiated, plug in 0 for t. When I plug in 0 for t, I'm actually going to have this also that I'm going to have 4 over 6 e raised to power 2 into 0. Then I'm going to have 9 over 6 e raised to power 3 into that. Okay, so don't forget, anything raised to power 0 is 1. That's going to be 1. Or this is going to be 1. Then what I'm actually going to have right now is going to, I'm only going to have 1 over 6 plus 4 over 6 plus 9 over 6. Okay? Now, when you have that right now, oh my God, you are back at elementary school. You remember what you normally do in elementary school, where you do addition of fraction. So right now, that should be like 14 divided by 6. And don't forget, you need to simplify that. Oh my God. Simplifying that will be 7 over 3. And that was why you got the 7 over 3 here. That's how we figure it out. Let's put the value of y is 7 over 3. Is there any question? Okay. Silence implies you get what I mean. You get what I. Okay, that's how we go. That's how we do that. So, how do we do the variance? You're going to follow the same process. Okay, have different getting the variance now will requires that you do the second derivative minus. Okay, so if you want to write the formula out, okay, the formula here is going to be expectation of y squared minus, okay, expectation of y or squared. And of course, a moment generating function, it means differentiate the moment generating function twice. Okay, of plugging 0 for t minus when you differentiate once, okay, and you square that, okay. Of course, we've already gotten 7 over 3 out, okay. Then we just need to square that, but we need to work on this by coming back again. What you've differentiated before, you're going to differentiate it again, and after differentiating again, you're going to plug in 0. So if I were you, can you show that after differentiating twice and I plug in 0, what you're going to get is going to be 6. This guy here. You can try that. Okay, you're eventually going to get 6. And when you simplify all of that, you're going to have 5 over 9, which is going to be, the variance. And of course, if they ask you to find the standard deviation, don't forget you're going to find the square root of that. Okay? Okay, so you can try that. Okay? The answer is already there. Okay? Now, the next question said the distribution of y. Oh my God. There's something I wanted to see. If you actually want to obtain that distribution, take a look at this guy. Equate this guy to, because that guy means expectation of e raised to power t y, which is summation, e raised to power t y. The probability of y equal to that And y in this case, where is it going to start from? If you take a look at this, ty. Here I'm having only t, though that actually implies my y is my y equal to 1. And here that I have raised to power 3t, okay, that means I'm actually going to end up in 3. So the way it is right now, the random variable will be 1, 2, 3. If you want to know that, you can check what because you can see exponential raised to power t y here, and this is raised to power t, raised to power 2 t, raised to power 3 t, then which means the coefficient of t is going to be the respective random variable. That's why it's going to be 1, 2, 3. And you know what? Oh my God. The moment you have the 1, 2, 3, now, okay, when y equal to 1, it starts when y equal to 2, when y equal to 3, and what you can do, you can actually, so which means the probability section, it is this guy here. Okay, give me 1 second. Oh my God. When you take a look at this guy, the section is 1 over 6, 2 over 6, 3 over 6, which is what we have here. Now, if I want to write the distribution out the way I normally do, okay, if you go by what I did in class, if you go by what I did in class, oh my God, if you go by what I did in class, this is what you're going to have. I'm actually going to have a table. I'm going to have this guy. Okay, so I'm going to do y. I'm going to do probability of y. And now I have 1, 2, 3. Then I'm going to say, okay, this is 1 over 6. The probability for this is 2 over 6. And the other one for is 3 over 6. This is what they mean by probability distribution. Okay, and that's all. That's how you're going to get that. Any question on that before moving forward? Okay, so because of my time, I'm actually gonna move. Now we're back at continuous. We started continuous distribution this week. Okay. Now the proportion of time, why that an industrial robot is in operation during a 40-hour week is a random variable. Okay, with probability density function. Okay, it is not all the time that industrial robot is in operation. So, but mathematicians have been able to figure out what the probability model is. Okay, and they said, oh, f of y is going to be 2y. Okay, of course, the state space of y is going to be from 0 to 1. Don't forget, I'm actually talking about proportion. And of course, it said, oh, it is not defined if the range is x-way, like if it is not between 0 and 1. Now, from any probability model, okay, we actually want to figure out what is the average. And the moment I get the average, how can I actually rely on the average? Okay, if I want to know how the data have been dispersed, then I need the variance of y. Okay, so now and question B is now defining a new variable. Okay, if x is a function of old variable y, so can I figure out the mean of that as well? You remember the linear combination. So if I want to go by what I did in class, of course, here, this is the solution. So you just need to know for a continuous random variable, it's going to be integral. If I want to find the mean, it's going to be integral. Here is 0 to 1. Okay, y. Okay, f of y, the y. F of y is 2y, so I'm going to do y to y. So, y multiplied by 2y, so it's going to be 2y squared. Okay, that was why you see 2y squared here. Integrating that over 0 to 1, that is going to give you the mean that we have. So the mean is going to be 2 over 3. Now, if you want to get the variance, you need to first figure out the expectation of y squared. Don't forget that. You remember, okay, the variance of y is expectation of y squared minus expectation of y or squared. Okay, and I've already gotten the expectation of y to be 2 over 3. And now do I want to get the expectation of y squared? Expectation of y squared is going to be integral y squared f of y, the y. And that's going to go from 0 to 1. And what is your f of y? Your f of y is 2y. So I'm going to do 2y times y squared. That's, times y. So now, we have a 2y here. Okay, 2y times y squared is going to be 2y3. you do algebra before you do calculus. Okay, so then you integrate that, then you get that over the range, you're going to get that, then you actually use this guy, then you're going to get your variance. Okay, now after getting the variance, now you've gotten the expectation of y, which is the mean of y, and you've gotten the variance of y. Now, the next that you want to do right now, you actually want to figure out this guy. Oh my God. You know, the robot on that study, the profit X for a week is given by 200Y. Of course, if you take a look at what they have here, X represent the profit. Okay, so right now, so if I want to find the average profit, because profit is a random variable in the stochastic world, so I'm going to do expected value of S will be equal to the expectation of 200, Y minus 60. Okay, so it's going to be 200 expectation of Y minus 60. Of course, you've gotten the expectation of Y here. You just need to plug that in. That is exactly what I'm doing here. And at the end of the day, that give me that. Take a look at that. That give me that. Now, if I want to figure out the variance right now, I want to find the variance. Okay, so how am I going to figure out the variance? Okay, I want to figure out the variance of S. Okay, so what I'm going to do, the variance of 200 y minus 60 is the same as the variance of 200y because variance of a constant is zero. Okay, and of course, the 200 is a constant. 200 is going to come out, going to be 200 squared variance of y. And you have already obtained the variance of y to be 1 over 18. Okay, so you're going to plug 1 over 18 here, multiply by 200 squared. Okay, and that's exactly how what we do to get this guy here. Okay, so that's how to do that. Okay, so because of my time, I think I'm going to spend 10 more minutes. But for those of you that have class, you can log out. But this is being recorded. You know, you can log out at 9:55. Okay, so I have not taught Shep in this class, so you need to ignore C. Okay, now you remember we talked about normal, okay, and we talk about uniform, right? So let's take a look at this. You know, when they give you a problem for under continuous random variable, they're going to tell you the distribution. But if you're giving question under discrete, you're going to be the one that will figure it out. But right now, they've already told us here, uniformly distributed with between 20 and 25, and they wanted to find probability of the low bid on the next interstate shipping contract is going to be less than 22,000. You remember when S follow uniform or unif with parameter AB. You remember that the F of S is actually going to be 1 over B minus A, where B is the upper bound, A is the lower bound. So right now, your 25 is going to be upper bound, your 20 is going to be lower bound. So what is my F of S? So my F of S is going to be 1 over 25 minus 20. Don't forget, this 20 and 25 is in thousands of dollars. Okay, don't forget that. I can decide to work with to just 25 and 20. Okay, so that's going to be 1 over 5. So the probability is 1 over, the function is 1 over 5. Right now, I want to calculate the probability of below $22,000. You know, I want to do probability of X less than 22. Okay. The probability of S less than, oh my God. I'm going to start from 20, which is the lower bound to 22. Then I'm going to do 1 over 5 ds. Okay, I'm gonna do 1 over 5 ds. So when you do 1 over 5 ds, so you have x over 5 after performing an antiderivative, then 22 to 22. So you're actually gonna do 22 minus 20 divided by 20. Okay, that's gonna be what is two? Let me see. You're going from 20 to 22. Okay, so that's gonna be 2. Okay, so now if you take a look at what I have, oh my God, sorry, that was an error. It's gonna be 5. Okay, here, that's the 5. Then you plug in 22 minus that. So that's going to be 2 divided by 5. That was how we got this 2 over 5. Okay? And in decimal, that would be zero point 0.4. And you can also compute greater than. Okay? So if you want to do greater than, so like great, he said in essence of 24. Okay, so in essence of 24. Okay, so this guy means I want to figure out the probability of s greater than 24. So if s greater than 24, it means I'm going to start from 24, then I'm going to end up in 25, then 1 over 5 ds, which is going to be x over 5, 24 to 25. Okay, so which is going to be 25 minus 24 divided by 5, which is 1 over 5. That's why you have that guy. That's super easy, right? And what if they also ask you to find the mean? Okay, don't forget that you can be asked to find the mean. The mean is going to be b plus a over 2. Okay, 25 plus 20 divided by 2. What if they ask you to find the variance? Is b minus a all squared divided by 12. Don't forget that I gave you the formula in class. Okay, so super easy, right? Super cool. That's super cool, right? Now, I want to move right now. Okay, like this is 9:55. For those of you who want to go to another class, you can log out, but I'm still going to be here for 5 more minutes. Now, uh, the next question asks, what is the median of a normally distributed random variable with the mean mu and the standard deviation sigma? Now, let me tell you this. Well, for situation where you have a normal distribution, okay, if y follow normal with the mean, and that's where you have f of y equal, f of y equal 1 over square root of 2 pi or sigma squared exponential raised to power this y minus mu over sigma or squared. Okay, where your y's take a value from negative infinity to infinity. Now, the median, and the mode, they are going to be the same. But if you want to find out, okay, if you find the probability of y less than mu and probability of y greater than mu is going to be 0.5. Because the total area under a curve, because we expect that this plus this should be equal to 1. Okay, we expect that should be equal to 1. Okay, so now you can try that. You can try it to see if you actually perform an antiderivative on this, where you want to find the probability of y greater than mu. Okay, you want to see whether you're going to end up in zero point 0.5, and the way you can do that. Okay, the way you can actually do that, okay, the probability, give me 1 second, the probability of y less than mu, for instance, okay, you integrate this guy, okay, now less than mu from negative infinity to mu of dy, okay, you can try that. I will give you 0.5. And if you want to try this, okay, you can standardize. Okay, you standardize z is y minus mu over sigma. Okay, so if you standardize, you'll be able to make use of a table. That would be super cool. Okay, so that's exactly what I mean. Okay, so so far so good. Let me see what I have left. I'm actually want to see what I have left. Okay, so what do I have left? Okay, so oh, this is easy peasy. Okay, calculation involving normal. I told you, where I show you stuff like this in class. Okay, they wanted to figure out the probability. So wires manufactured for use in a computer system are specified to have a resistances between this and that. The actual major resistances of the wire produced by a company have a normal distribution with a mean of that and the standard deviation of that. What is the probability that a randomly selected wire from a production will meet this specification? So meet the specification is okay, the random variable y lie between 0.12 and 0.14. So which is what you see here. And what are you going to do? You standardize. Don't forget, you're actually going to standardize using, okay, you standardize using z equal y minus mu over sigma. Okay, so standardizing 0.12, that's what you're going to have. Standardizing 0.14, that's what you're going to have. And which means the probability, okay, if I actually want to find the probability of y lying between that, it is the same thing as the probability of a z lying between that. I told you in class that standardization, facilitate easy probabilistic computation. Imagine if I want to solve this without standardization, I'm actually going to run into rigorous calculus, and that's why standardization will make your computation easy. So right now, so this is just going to be, oh, go to the table. Okay, what is the probability of a z less or equal to 2 minus the probability of a z less or equal to negative 2? Okay, so when you check from table, check that from table, subtract them, you're actually gonna have that. Okay, so that's how we go about that one. Now, I think that B part is gonna be the last question of the day. Let me see. It's gonna be the last. Let's go to B part now. Now, the B said if four of these wires are used in each computer system and all are selected from a company A, what is the probability that all four in a randomly selected system meet the specification? Now, when you say the probability that all four, actually meet, the specification, okay, so what you're going to do is, can we define our random variable? Okay, now the random variable numbers of fire that do not meet the specification, because if they talk about meeting specification and not meeting specification, you know, that is a binomial process. Because the binomial is characterized with two possible outcomes. So, that's why I need to define my random variable S now. Okay, now because of the curve that's going to follow binomial distribution, and of course, and here you've been told that you have a sample of four, so n equal to four. And what is the probability of, associated, with that is what you computed here. And that's why you see that guy now. Now, I want to find what is the probability of S, equal to four. Okay. Now, the probability of S equal to 4 is actually, using the binomial probability. And don't forget, binomial sampling with replacement, which means they are actually going to be independent. So the probability of S equal to 4 is more or less like raising this guy to power 4 because they are independent. Okay. Then finally, I'm actually going to get that. Okay. So I want to thank everyone, for attending my lecture today. I think I was kind of down before, but I think I'm getting myself back on the track, So, um, is there any question on everything that I've said today before I go? Is there any question? Okay, so in the absence of question, I want to thank everyone for attending. Oh, let me see. I think I have a chat coming in. Let me see. Oh, okay. Now, if you really understand what I've passed across today, I need you to say yes. I need to say yes, or you comment yes. Or so I want to hear from you if you understand what I've done today. If you understand what I've done today, I need you to say yes, or you comment yes. And if you don't understand that, please ask me a question before I go. Okay, I can see shots coming in. Okay, okay, okay. Somebody say, yes, I understand everything. Okay, thank you so much. But in case if there's anyone who is struggling who doesn't understand stuff, please make sure you reach out to me during my office hour or you reach out to my TA. Okay? Um, that's all what I got. Make sure you all stay safe and have a lovely weekend. See you on Monday. Bye for now, everyone.